My name is Rainer Grimm. You see it here. I'm a C++ or programming consultant since the last millennium, so quite a time. In 22-24, I created a further education group in my company, and this was the starting point for me as being a trainer. Since 26, I don't know it so exactly anymore, I give C++ and Python classes at this point in time for a company. 2013, I changed the company. No, this is too much about me. Anyway, since 2016, only the main points, I'm an independent C++ and Python trainer, and I'm quite happy with it. And now I'm also developing a worldwide mentoring program, which will start next month. Okay, this is all what I want to say about me. If you want to know more, ask me later. I'm a little bit irritated by the light, but anyway. Okay, this is the plan for today. I called it the hidden or small pearls. Anyway, how you would call it. This means I talk about all the stuff excluding this one, the big fours. Concepts, modules, ranges, and coroutines. I already gave talks about them, and you cannot do it in 90 minutes. So let's talk about those not so big, no, the small other ones. By the way, these are not all features which I should mention as C++20 talk. There are more than that, but this is at least the stuff you should know. I talk about the core language, about the library, and about concurrency. About the three-way comparison operator, designate initialization. We have more ways to express constants in C++20. A few templates and lambda improvements. Then I come to Standedspan. A few very interesting container improvements, such as Constexpr vector. Few arithmetic utilities. This is a lie. This is not a small pearl. This is a big, big pearl. In my book, it required me at least 80 pages to describe the times and library or Chrono facilities we got additional with C++20. This is a big, big stuff. But anyway, I will do it short here. I talk about the new formatting library, which we have since C++20. This was the library stuff. And then we switched to concurrency, a few nice additions or improvements to atomics, semaphores, which we now have, about latches and barrier, a simple synchronization mechanism, about cooperative interruption, and finally a little bit about G-thread. Be careful, G-thread, not thread, G-thread. Okay, let's start. I have in my slides many code examples, meaning when you have my slides, just use them. You will be redirected to Compile Explorer and you can see the stuff live. With two exceptions, all of the stuff is working, I'm presenting. Okay, let's start with the core language. We have the three-way comparison operator, meaning you can use this special operator here. Oh, this is a little bit small, you see it here. Oh, I'm also too small, which is called spaceship operator. I assume you know why. And this will create you the 6 relational comparison operators. You can do it by yourself, or you can default it from the compiler anyway. And you need the header compare to use it. They are implicitly Constexpr and no except, meaning they could run at compile time. And they compare their elements lexicographically. What does it mean? When you have a class which has attributes and has base classes, all attributes are compared in their declaration order in all base classes from left to right if you have multiple inheritance. This means lexicographical comparison. You know lexicographical comparison, sorry, a terrible word. When you look into a phone book, this is what you do. You start with the first letter, then you go to the second, the third. This is lexical comparisons. And here you do it the same. What should I say additionally here? No. There's a small exception of the lexicographical comparison. This is regarding to equal and non-equal. Here you first check, are they both have the same length? If not, you know they cannot be equal. So there's a shortcut here. But anyway, essential lexicographical comparison. Sorry, I could not even pronounce this in German. Okay. No, don't laugh. My int, here I use it. I have my int, which is a small wrapper around an int, and you see I have an explicit constructor. And now what I do here is I implement by myself the three-way comparison operator. And what I do is exactly I apply it to my member. What should I do otherwise here? And this one I can use. Essentially, this operator returns three different values. Something smaller than 0, 0, and something bigger than 0. Three states. But I can also do it in a more lazy way, and I can ask the compiler, please do it for me. Once more, this one is Constexpr. This one not, because I forgot it. Okay, this one returns your strong ordering. This one returns your partial ordering. Strong ordering essentially means each int can be compared with each int. So this is strong ordering. Partial ordering means there are doubles available which cannot be compared, such as none. Therefore, you only get a partial ordering. In between, we have a relationship which is called weak ordering. So the compiler automatically generates the appropriate ordering ideas or concepts. I don't know how to say it. Not concepts, no concept sense, sorry. Okay. Here's something very, very interesting, which is nice. When you do something like a smaller b, the compiler rewrites it to this expression, and this is what the compiler is doing. So the compiler applies implicitly the three-way comparison operator. And here's the nice observation. When you do a smaller b, and this is not available, the compiler rewrites it to be bigger than a, essentially. You see? So they are switched, the order is switched, and you do it from the other way, from the left to the right, and then from the right to the left. So the compiler rewrites here this stuff, which makes a lot of sense. If not, you would have to implement it in two ways. Once from the left, once from the right. And as I mentioned to you, I have many code examples, but I have an issue here, a place issue. Let's see if this works. So once more, when you use that, and you have an internet access, which I have here, yeah, I see. This is maybe too small, so let's make it a little bit bigger. Wait a second, is it big enough for you? Only the people in the last row count. So is it big enough for you? Say yes or no. Yes, okay. So I have to remember 18. And here you see, I have a class. This is the same class as before, just used. Then I have here a generic is less than function, which takes 2t and compares them. And you see t, t2, this both types can be different. This is what I want to use. Now I have a Constexpr my int and a Constexpr int. Now I can compare them in any way. I can compare two my ints. I can compare an int and my int. I can compare my int and int. And here's the proof, it's done at compile time. If not, the compiler would complain here. I enforce it, do it at compile time. I want to have it. And this is how it works. And this is the result, which is not so thrilling. Okay, this was three-way comparison operator. Maybe you know we have since C++ 98 aggregate initialization. Essentially, aggregate is a C data type, a C array, sorry, or a class which a typical layout or typical structure, meaning no user-defined constructor, all members are public, no virtuality of members or base classes. This is essentially aggregate. And now what we can do since C++ 98 is you can directly initialize these members, such as you would initialize a C array. So far, nothing interesting. But here comes a nice feature which reminds me a little bit to Python, which is now you can initialize them. You have, see, I have here an aggregate, and now I can initialize them just using the attribute names. And you can also provide default values. And if you don't provide the initializer, this member gets the default value. And what is also here detected is narrowing conversion. Meaning, when you would make nonsense, such as providing here double, but this is an int, which would mean narrowing conversion. Conversion with loss of data accuracy, the compiler would complain and you would get a compiler error. So this stuff detects narrowing conversion. Okay. Let me show you this example once more. You have all of this stuff available. Afterwards, you see here, I have a point x, y, z. I just display here these values, p, x, y, z, sorry. And now I can initialize it with x, y, z, which is fine. Here I can here call the default constructor, meaning y and z have the value 1 and 2, but x is not initialized. As the standard says, it's initialized to an arbitrary value, which is crazy for me. It's not initialized, point. But out of strange reasons, I got here the 0. If you don't believe me, read my book. You see that there could also be a different number here, of course. Okay, once more. I can only initialize x and z. But what you cannot do in contrast to C is to change the order of initialization, for example. You see, Z and Y, this is not allowed in C++, but this would be possible in C. Okay, nice feature. Once more, reminds me a little bit to Python, to named variables, but it's not as powerful as. Okay. I have little issues here finding my spot. Consteval. Okay, what is consteval? Consteval generates a so-called immediate function. This means a function which can only run at compile time. Once more, only at compile time. We have 3 different kinds of functions. We have usual function only running at runtime. Constexpr function could run at compile time, could run at runtime, and now we have constable, only runtime. Only compile time. Okay. You cannot apply consteval to a destructor function which allocates, has the same requirements such as Constexpr I mentioned in C++ 14, not in 11. And here you are. Have a look. This function can only be executed at compile time, meaning this is fine, but this is not fine. Why? Because x is not a constant expression. Therefore, it cannot be used in a constant expression. And this would give you an error. Once more, only compile time. However, I gave at the CPPCon a talk, a 1-hour talk, only explaining how many flavors of const we have in C++ now. This is constinit, second flavor. Constinit guarantees for variable with static storage duration, meaning something which is static, external, or defined outside any function scope. You can initialize them at compile time. And here's the extremely interesting point. They are not constant. So you can initialize them at compile time, but they are not constant. And they avoid something which sounds a little bit terrible, static initialization order fiasco. Sometimes also called problem, but for me it's more fiasco. See what I mean by that. Have a look. The essential point is the following. Let me rephrase it. You have 2 statics in different translation units. One translation unit is all what you get after the preprocessor runs. One in one translation, one in another translation unit. And now one needs another to initialize themselves. Now you have a dependency. And what we don't have is a guarantee which one is initialized first. With 50% guarantee, you will get the right result, or you can also say the other way around. And here's, have a look. I have a static A, you see here, which requires the square B, and this is here. This is static B, which is dependent on static A, meaning static B requires that first static A is initialized. Here I have a dependency, you see, 2 translation units. Now I compile it in 2 ways. Have a look. I compile both programs, you see, the left one and the right one. And now just for fun, of course, this is not well defined what I do here, but you see at least the effect. What I just did here was, I linked it in different sequence, you see? And depending on the linking order, static B has the value 0 or 25. This is the static initialization order fiasco. And the same goes for destruction, but here it's initialization. We don't have a guarantee. And constinit will solve this issue. Just make it constinit. Now it's initialized at compile time and you are fine. Small template and lambda improvements. First of all, now we can use templates with floating point numbers, initialize templates with floating point numbers, which is new. So so-called non-type template parameters can now be floating points. And you can also use classes with Constexpr constructors as template arguments. And this looks for a few people a little bit strange, but now you can do it. You can have a templatized lambda, you see? What does it mean? I want only to have a vector. What could be generic is my element type. So I say I only want to accept a vector, but I don't care which type the vector has or which elements the vector has. And this is something new. You may think this makes not so much sense, but anyway, let me show you something. Wrong button. This is a little bit difficult here. Here we are. Once more, example. Let me make it a little bit bigger. Only to see the difference. This is a lambda we have since C++11. Only accepts in specific type, or in this case, 2 types. This is a lambda we have since C++40, which is essentially a generic function, accepting arbitrary type for first and second. And now is the new stuff, you see? What I require here is the type can be arbitrary, but both should have the same type. And not impressed? Then look at this example. Here I have a lambda taking a stud vector of t, meaning this would work. Have a look here. Lambda vector, this is my lambda expression, accepting as argument my vector. It's a vector. But when I would use it with a deck, this would fail. Because a deck is, of course, not a vector. You can even use here, which is extremely nice. I should not say anything about the big 4, but I cannot hesitate. You can even use here a concept, which makes it extremely elegant, for me at least. It just works together. Okay, let's continue. I'm a little bit irritated. I have 3 controls in my hand, and this irritates me. Oh, this was it about the core language. Let's skip to the library. Standedspan. Standedspan stands for an object that refers to a continuous sequence of objects. It's essentially a pointer and a size. I only talk about a dynamic span with dynamic extent. A span is never an owner. Essentially, you could also call it a view, which you may know from different contexts. The referenced objects can be an array, a pointer with a length, or a stud vector. It could also be a stud string, but in this case, I would say use a string view. Okay. It allows you to partially access the continuous sequence of elements. And now see what you can do with a Standedspan. This is my favorite example. This is totally error prone. This is by design broken. What is by design broken? How you accept a C array is by design broken because you get a decay. This means you have a C array, and what you get in a function is a pointer to the first element. And if you have when you have a bad day, you miscount, and now you have undefined behavior. And here, this is different. You see, I have a function taking a Standedspan of int. Now I can invoke it with an C array, with a stud vector, or with a stud array. And this is not a generic function, but it looks like a generic function. Have a look. Now this Standedspan deduces the size of my C array, which is nice. You cannot miscount by design. And you see, the C array has 4 elements, which is not so complicated, but anyway. And this is, for me, extremely nice, and this removes all of this ugly decay error we have from our legacy code bases. Yeah. Not interchangeable. A string view is essentially a string. A string has additional semantic. But my point was a different one. You could also use here, when you would have a vector span of chars, use in stud string to invoke it. This is my point. I honestly, good idea. I never tried it out. Guy, do you have an idea? Any idea? I don't know it. I never tried it out. But I just tried out to use with Standedspan a stud string, and this works. This was what I tried out yesterday. I assumed it should work. If not, it would be something I would be a little bit astonished anyway. Yeah. Honestly, I never tried it out. I only use this syntax here. Good point. I'm not so the big fan of C arrays, so this is maybe one of my weak points. Okay, thanks. So, once more false button. Let me go back to my presentation. But you can do, oh, wrong. But you can do also additional interesting stuff. You can modify the underlying container. You reference something, you view something. Have a look, I have a vector of 10 elements. And here I just display them. I show you the program in 5 seconds. Now I create a span of this vector. So far, easy. Now I create a second span, which took this span here, but not all of it, only starts with the first and ends with the second last. I'm not sure if this is the right expression for it, but you know what I mean. So not the entire span, a subspan. And now I transform this span here. Have a look here. I use stud transform from the C++ library, say from begin until end, and map each element to its E to its E times E. And I put the result back to span to begin. And now you see the change in vector, and you also see the change in span 1. So you can, I show you the example, maybe this will answer the question. If not, wait a second. And now you see, oh, wrong button. This is a little bit difficult here. Yep. Here we are. I now make this a little bit bigger because now this is too small. Where's my button here? Stem. Here we are. So this is my original vector, you see, 1 until 10. And now I just, you see, I just take the elements from the second one until this, not the last one, and this one before the last one, and I map them to its E to each times E, you see it. And therefore also vec is modified and span 1 is modified, and also, of course, span 2. You had a question? First start with one. Which deck? A deck is not a continuous sequence of elements. This will not fit into this. It should be a contiguous sequence of elements, contiguous memory block. This will not work. Second question. I don't know exactly what you mean. Can anyone kick in and help me here? I assume you should have a vector which meets. I don't get you. It's a view. This is why I said it's a view. This is also called a view when you regard it from the ranges perspective. We have different views. We have a string view, which is called view, and this is called span, which could also be called a view, but anyway. With two exceptions, I don't have it in my mind. String view is a 17. There's a prefix and suffix additional member function, which allows you to reduce your view on the underlying string. But essentially, right, a string view is something constant. This is essential. It's essentially a string, and what is only left is the constant, the reading part of the string interface. You're right, yeah. So it's a little bit different, of course, but anyway. This is the point of this example here. This is the point. And here I use two interactions, not only one, two of them. So vector to span 1 to span 2, and then I modify span 2, which was reflected in span 1 and also in the vector. Okay. Let's continue. Container improvement. By the way, this is maybe for me the most astonishing new feature in C++20. Not the most, how should I say it? The biggest one. We have now Constexpr vector and Constexpr string. Meaning all member functions of the vector and of the string are now Constexpr in C++20. Additionally, all algorithms of the standard template library are Constexpr in C++20. What does Constexpr mean? It gives you the potential to execute something at compile time. Only the potential. You can even use it at runtime, therefore it works the way it worked before. But you can do it at compile time. And what you can do is the following. Not this one, then. Here we are. Have a look here. Let me make it a little bit bigger. And now let me show you. First of all, the values are small, but you know what I mean. Have a look. This function is Constexpr, meaning it has the potential to run the compile time. I create a vector. I sort this vector, and then I return the last element, which is the biggest one. Once more, compile time. And here you see, here's my proof. Max element. I want to have it at compile time. If not, the compiler would fail here. Compilation would fail. And here's the result. Once more, not so thrilling. 4. And I can also do it with a 70 feature, which is a Constexpr lambda, you see? a context for lambda. Here. In place invoked. It's essentially the same stuff as here above. And once more, you can do it for vector and you can do it for string. There are a few limitations, but anyway, you can do it. Container improvement. Ah, yeah, you know it. When you teach C++ and you say, how can I remove something from a container? You have to explain this strange erase remove idiom. Because remove only returns to the logical end of a container, not the physical, and therefore you have to do it one additional step. And now in C++ 20, you can do it in one function call. Std erase or std erase if. Most of the time when it's called if, it needs additional predicate, which in my case is now a lambda. And this is what you can do. Have a look here. And this is quite convenient. What I do is the following. I have a string with a few characters only for testing purpose. And I say remove all of the stuff which is upper. Just using a lambda expression as a predicate. And I started with only for testing purpose and I end with you can read it. I don't want to read it. Which is extremely convenient. These are only small features, but anyway. Yeah. What are special? I don't get you. Honestly, I don't know it, but I would strongly suggest that you look inside the implementation, and I assume this will be available as CP reference. Here's a possible implementation, then you can see it. I assume that this should be an extremely small function, and maybe only a wrapper around erase remove. I don't know it. Yeah. But you can overcome it quite easily. You can dispatch on a on text. You can dispatch on concepts. You can dispatch on concepts. There are so many ways to overcome it. And you know, C++ is optimized for runtime. I assume there's, but I don't know it honestly. Just look it up, and I'm quite sure. Okay, erase upper, I did it. So let me continue here. Small convenience function just for strings, starts with prefix, ends with prefix and suffix, and you can remove it from a string. Just a few additional functions a string provides, or improved interface. Yeah. What I often say in my seminars is don't use signed and unsigned in an arithmetic expression. You may not get what you expect. And with C++ 20, we get this guys here, you see? Compare equal, not equal, less, the sixth relational operator. Let's see what's happening here. Once more, the general rule, don't use signed and unsigned in an arithmetic expression, such as here in comparison. And here I have a signed -3 and an unsigned y, or 7. And when I compare it, -3 smaller than 7, it says false, which is a little bit strange. What is happening here? I don't know why, but this int is converted in this expression to an unsigned int. Just look, use this code and use the CPP insight, and you will see what's happening under it. And this is really astonishing, but not with compareless. Here it, how should I say it, respects the signedness and unsignedness of the underlying ints. Once more, if you don't believe me, use this button here. Then you see what's happening in the first line. Okay, new arithmetic utilities. You see a few constants. We have them. This is all what I want to say. And now to a really, really big feature. Once more, I needed more pages to describe calendar and time zones than for my explanation of coroutines in my current book. This is a big, big, big feature, really. And it would take me at least 1 day to explain it. I have to say, I could not explain it. I think the only one who could explain it is Howard himself. This is really a challenging feature, but it's also a powerful feature, typical for C++. So we have chrono or time functionality since C++11, and with C++20, this was improved a lot. We got new clocks, you see? We got a new data time, which is called time of day. This means the time since midnight. We got support for calendar dates and for time zones. And I don't tell you now the details because it's too much. I only want to show you 4 examples. Then you get a gut feeling what's inside here. These 2 examples here will not work, but they work. Wait a second. They will not work. Why? Because this is a Windows issue on the Compiler Explorer. I talked with Matt a few days before. And the issue is there's a query for a database, and this will give a timeout, and therefore we will not see anything. Locally, it works, so you see the result, but I have to go to my local PC. This is all supported by this Windows compiler, so there's nothing which I should fake here. Okay, time of day. And I honestly suggest that you study examples to get an idea how this stuff works, because it's quite heavy to understand. Here I created a time point, you see? I used the C++14 time literals. And I just added them together. Now I have the time of day, you see? And you see this is right. Oh, this is not right. I'm just in Germany, I assume. Anyway, you see? Oh, this is strange. Oh no, this is the PC the compiler Explorer is running on. Sorry, this is always strange. But I think you believe me, it works. And now I can ask for the hours, minutes, seconds, and subseconds, you see? Since midnight. And here the duration in seconds resolution. And I can create the same, how should I say it, time of day data type when I just provide the seconds. Sorry, I said something nonsense with no sense. My point is I provided the values, so there's no reason. You see, I just displayed this value. This is time of day. And when you look from this perspective, it looks quite nice. What you can also do is the following. Cute syntax. This name is by Howard. And this is a cute way to create dates. And here I created dates. It will take a few seconds. I create dates. It's my birthday to remember it. And here I have a look. I started with year, with day, and with month. Meaning I can compose. I provide here an explicit data type and date. And from that data type, this both are the missing one are predefined. I don't know how to say it differently. There are 3 ways to create a date. You can start with a year, and a day, and a month. And the reason for these 3 ways is quite simple. These are the typical ways to do it. And therefore, these 3 ways are supported. And now you see, I use this slash. This is why it's called a cute syntax, because it's cute. You can do it in a more elaborate way using this syntax, but I did it this way. And here, when you do something crazy, you see, I specified the 26th month, which is not known in Germany. And now I got the answer, it's not a valid date. So this is an extremely easy way to specify a date. And now to the 2 examples, which I cannot do here because of a timeout reason, because of a database query. But first, you guy. I don't care. Once more, the point is here. Wait a second. This is Windows. Windows always takes a extremely long time on the Compile Explorer. This is not due to this example. This is due to Windows, to the Compile Explorer environment. Honestly, I'm not sure. I cannot answer the question. But you will see it with a simple Hello World program. It will take way longer with Windows, such as with GCC or Clang or any other compiler. This is due to the setup here. So I don't know. Yep. Honestly, I don't know what this means, but it just gives me a hint. This is not valid. Good point. You have to look it up. What you see here is it's worth no exception. It just gives you a message. This makes no sense. I'm not 100% sure. You have to write Howard an email and ask him probably. Now this is the one who was the designer behind this feature, and I know it. 2 hours. He gave a 2 hours talk. First about time of day, and then about calendar or something like that. Was it here? So it was here. It was a CPPCon. I don't know it. I know this talk. I watched it. But you see, no exception. Okay. And this is what you see. This is essentially a timeout. And this is due to this function here. Therefore, I will show you the result live. This is due to this function here. Because here is a database query involved, and this will give me a timeout. So I have to do it locally. But first, let me compare both. Here's the program, the output of this program, and you see it here. Let me make it a little bit smaller. Is it readable, the black stuff? Once more, not the people in the first row count. Okay. What I do here is, you see, I have the current time. This is a C++11 feature. Then I displayed rounded to seconds, you see. First I displayed without rounding, and then I rounded to seconds. So far, nothing special. This is a stood chrono floor. Then I make a zone time. Have a look. This means the following. Oh, this is a little bit complicated now, but I will handle this. I make a zoned time. Let me explain it. So I use this UTC time, and I say I want to have this time in my current time zone, which is now the time zone of the Compiler Explorer. I don't know where it runs. And here's the result. Here we are. Meaning in the current time zone is 15 after 10, whatever that means. And now what I do additionally, local time. Okay, I display the local time. And here the offset to UTC. And you see, we have here an offset of 60 minutes or 3,600 seconds. So, and now to the most interesting example. You know, I give many online seminars. And you know what is always the issue? When should they start? When should they end? I have people from Australia and from the US, and this is quite difficult, you see? So I created a small program, which I call online class. Wrong button. Then you see what's possible with this feature here. I only give you an overview of the program, and then I show you the result. I want to know for different time zones, and I made this program in the past. For different time zones, you see, these are the time zones. When I start in Germany at 7 o'clock, 1 o'clock p.m. and 5 o'clock p.m., which time is it in these time zones here? So I just invoke this function and I iterate through each time zone here. Because I want to know what is the ideal time when I have people from different time zones. This is not an easy problem to solve. And what I do essentially is here, I will not go into the details. I display my time zone. You see, zoned time. This is my zone. Here's when my training starts, and here's when I add the duration of my class to it, which is 4 hours. And now I display all values depending on the time zone I use. You see, here I iterate through each time zone, and then I evaluate this value for each concrete time zone. And here's the result. When I start in Germany at this point in time and at this point in time, in Los Angeles was the day before, and you see what this means for these different time zones. And this is, for me, extremely convenient. It's not so easy to build, but it's extremely convenient. And then I could decide I should do this start this at 8 in the morning or at 20 o'clock in the evening or PM, something like that. I only have to mention my CPP talk was at 10 PM in Germany. So you see, sometimes it's a little bit difficult. So this only gave you an idea about this extremely powerful library. What you can do with it. Time zones, calendar, time of day, discrete syntax, and stuff like that. But you can morph it, you can subtract, you can calculate this. There's a lot of stuff here involved. But for once more, read, study examples, and try to get an idea of it, and then improve your knowledge. Because it's really, really challenging. But I have to be honest. Time is for me the most challenging concept we have in general. What is time? I don't know. No, when you have a time point, you need a time duration and you need an epoch. Each definition depends on each other, which is crazy. Okay. Next part here, formatting library. It's something similar to printer family, and what you can do in a Python-like syntax, you can format stuff. You can specify fill letters, sign for numbers, specify width and precision, and specify the data type. This is extremely convenient, and here's a few of the features, and then I show you a few examples. You can say std format, which returns you a formatted string. Format 2, a string using a specific output iterator, and here you can specify the length of the string you want to have. All of the three functions follow the same syntax, so therefore you should only remember one of them. And I now show you format 2, which returns you a formatted string. And this is essentially the syntax, you see. You say what you want to display, and then you say what should be displayed. And these are kind of placeholders, the stuff in curly brackets. And what I did here additionally was, I specified here, I need the first one, I need here the second one. Therefore, the final string is hello world and not world hello, because I changed the order. And when you specify here after this 1 or 2 with a colon, you can specify a format specifier, and then you can say how it should be formatted. Essentially, once more, in the front, there's a string which is displayed as is, but you can use here placeholders or replacement fields, how it's called, and then you can do some stuff, which I show you in a few seconds. Okay. The question is, which data types can be displayed? Of course, the elementary data types, this is easy, but there are also the Chrono data types. So far, no compiler supports it. By far, the best compiler in this, with this feature is the Windows compiler, but not all the stuff is supported by the Windows compiler. Especially not when you want to display dates or times from the Chrono library before. But this is part of the standard. And what is extremely interesting, and this is also not supported by the Windows compiler. Once more, by other, it's not supported, but this feature only not by the Windows compiler, is you can write special formatter for your data types. And I will show you a simple example using in vector. You can nicely display in vector. And then you apply this format specification onto each element, which is what you want to have. Okay, only 2 examples. Once more, you have to study the literature to see more, to see how it works. These are only the small pearls, but you see they are extremely big. Here you see I did nothing, therefore is it readable? Oh, before I ask, I should make it bigger, sorry. But now you should study the output, which should help you. Okay, you see, here I just displaying it as given. Hello world 2020. Here I change the order. Hello world 2020. Here I say I want to have hello 2 times. I don't know why. And here I only want to have the first and the first and the third element. Hello 2020. Therefore, I just use this ID to say I want to have a specific element. And now to a more interesting example. I should say once more. So far, no compiler works with it. Therefore, I used here the prototype library, which is called FMT, which implements this stuff already. In some point in the future, I can change FMT to std and I'm fine. This is my idea. And let me display this. And this FMT library, as you can see it here, is pre-installed on the Compiler Explorer, which makes it quite convenient for me. And therefore, I can show you something. Have a look. I will not go into the details here, but what I essentially did was the following. I partially specialized std formatter, here's called FMT formatter, but you know what I mean, for a std vector of t. And what you have to implement is essentially the the pass function and the format function. The pass passes the stuff, and the format displays it formatted. I will not go into the details, but what I can do now, have a look here. I have here a vector of ints. Now I say just display them as they are. And this is what I should say, I put 2 brackets before and after. And a comma in between, you see? Now I said here, just use a plus before each element. Here, give each element 3 spaces, and empty space should be a 0. And here displayed in a binary format, you see? Only to give you an idea what you can do here. And the same goes here for a string. And here I say, the precision of my string should be 3. Therefore, this string I only left the first 3 characters. I only played a little bit with it. And in my book, I showed you a more interesting example, also in my blog, in which I had such a long vector of integers, and I layouted them. I made a line break after 20 elements or something like that. I introduced an additional symbol here, which is a pipe symbol, and I said after this pipe symbol, this number should be the indication of a line break. So you can quite elegantly display it. Once more, only an introduction here. And before the colon, you specify the ID. After the colon, you specify the format. And once more, this follows the Python syntax for a format string. Okay. Oh, wrong button. This is something which is really complicated here. Now let's talk about concurrency. Okay. I'm happy to say, or I'm not so happy to say, I recorded, I shouldn't have said, I don't like conditional variables. And with C++20, we have an extremely nice replacement. You can use an atomic flag, you can use instructor atomic, and even you can use a semaphore. But anyway, they are way easier to use and faster. So what we have here is a stud atomic and an atomic flag. And they got an improved interface. And you see, these are the member function names you know from a conditional variable. And you get a notify one, notify all, and the wait. And the waiting is here special. When the value of atomic is equal to the value of val, this blocks. This is the idea. And now let me show you how it works. I don't know if you know conditional variables. If you don't, maybe you know what a conditional variable is capable of. Spurs wake up, lost wake up, you need a critical section and stuff like that. It's terrible stuff, honestly. If you don't believe me, I wrote a post about it. And this here is a workflow which is typical for a conditional variable, which is a, how should I say it, a sender-receiver workflow. I have one thread which prepares work and one thread which waits for something to do. And of course, the preparation thread sends a notification and then says to the waiter, let's go, I'm done with my preparation. This is what first of all, I initialize atomic bool with false. This false would not be necessary here. It would default initialize to false, but to make it more explicit is fine. So I initialize it to false. And here's my waiter, have a look. Here's the guy waiting for the notification. And this blocks when atomic bool is equal to false. And as you see, I initialize it to false. So this waits. This waits until set data ready says, now I store a true inside atomic bool. and I send a notification. And this is the notification part. And this is only notify one. You can also do it with a one-to-many synchronization. Then you have to say notify all, but this is notify one. And once more, this is extremely easy to use. There are no reasons here for getting lost wake-up, spurious wake-up. There's no reason for using here some synchronization mechanisms, and so on and so on. It just works by design. And it's faster than a condition variable. I don't show you numbers. If not, read my posts or my books. Okay, with C++ 20, we got a atomic shared putter. Why? We have an issue in C++. You know my how should I say it? My favorite sentence from Tony van Oort. Forget what you learned in kindergarten. Don't share. Most important sentence about concurrency. And a shared pointer is by design shared. So we have a concurrency issue by design here because it's shared. Therefore, this needs a specific concurrency semantic. And now we have with C++ 20 an atomic shared pointer. These are two type defs. And the reason why we have them is quite easy. First, for consistency. Maybe you don't know it, but stud shared putter was, how should I say it, exceptional in C++ 11. It was the only non-atomic data type on which you could apply atomic operations. Most of you don't know it, but you could do it. And therefore, it was not consistent. This was the exception of the rule. Second, you can easily forget it, you see. Instead of atomic store, you can just say this one, and now you have a data race. Second issue, with the shared putter in C++ 11. And third, why we have it is, of course, you could make the shared putter by design atomic, but now you would optimize for the not so common case, which is concurrency. Therefore, we need an explicit data type. And now we have it. It's called atomic shared pointer. It could be log-free as far as I know. No implementation supports a log-free atomic shared pointer. I have to say it, only compiler so far supporting it is the Windows compiler, and the Windows compiler uses internally some synchronization mechanism such as a mutex. Okay, so the name atomic is a little bit irritating here. I know from Timo. Yeah. This would be nice because having a shared putter, atomic shared putter, is an extremely important feature for creating log-free data structures. Essentially, you need a log-free garbage collection, essentially, to implement that stuff. Okay, thanks. Semaphores, okay, we have semaphores in C++ 20. A semaphore is essentially something you initialized with a counter, and each one which wants to have this semaphore acquires it and decreases the counter by 1. When the counter becomes 0, the semaphore blocks each one who wants to have the semaphore. Sorry for the bad explanation. I will show you an example. We have a counting semaphore, and we have a special case, a binary semaphore, which could only have the values 0 and 1. Let me show you an example. And you know this example from before. This was this example about stud atomic. And here's the same workflow once more. Wait a second. Once more. Using semaphores. The same example such as before. You see, I initialize, I say, my semaphore should have the biggest value it should be 1, and I initialize it with 0. Meaning, here's waiting for work. Here I want to have this semaphore. I want to acquire it, but I don't get it because the value is initially 0. It stays 0 until someone releases it and puts the value from 1 to 0, and then this guy continues. And you see, there's here not even a notify. Just do it. And this is the same workflow such as before. I implemented with atomic, stud atomic, which I could also use as atomic flag, but this time I used semaphore. And this is my typical producer-consumer workflow. And I only want to mention, I was really, really astonished. I'm not sure if this holds for all architectures. On my PC, faster than a stud atomic. I was totally astonished. Once more, this ping pong game, only atomic flag is a little bit faster, but it's way faster than a condition variable when you want to synchronize something. And you see, this is extremely easy to digest. Acquire release. Semaphores. Fast way to synchronize something. Latches and barriers. Latches and barriers are a simple synchronization mechanism. It also is based on a counter, but here it goes the other way around. You know, the semaphore blocks when the semaphore is 0. Here it's actually other way around. It blocks when it's not 0. Okay, what you do is you have a latch, you initialize it with some number, and then then you can decrease this number by default by 1. You can wait. This just returns you how the number is. Here you just wait. You only wait when the counter is bigger than 0. And here you say arrive and wait. Means you arrive. You first count down the counter, and then you wait if the counter is still bigger than 0. Once more, you initialize with something with a value. I show you an example in a few seconds. You initialize with a value bigger than 0. Each thread which invokes countdown here decreases this counter by 1. By default, you can also use a different value. And here you only wait, and here you do both of it. You decrease and you wait. And a latch, good point, I forgot to mention it. A latch is meant for the one-time use case. You have one job, 5 threads should do, and when all 5 are done, all can go further. And then you establish a latch, which is essentially a protected counter. When you want to do it more than one time, a latch is the wrong data type. You should use a barrier. You see, a barrier can use more than once. You do it, make an iteration, then you wait until all are done, then you make a further iteration and further and further. And there's additional functionality here involved. And this is the following. In the so-called completion phase, this means when the counter is 0, a function could be invoked. In this function, you can do something special, such as changing the counter. This means when you create a barrier, you can also give the constructor of this barrier something invocable, a function, a lambda anyway. And this stuff is invoked when the counter becomes 0 in the so-called completion phase. So one thread is awoken, it performs this function, and then it continues. But this is the additional functionality of a barrier, which you cannot do with a latch. Once more, barrier for more than one iteration, latch for one iteration. Let me show you a simple workflow. I only use a latch here. But you see, this is extremely convenient synchronization. Oh, here we are. I have a few workers, you see. Herb, Scott, Bjarne, Andrew, and David. No, none of them is here, I assume. Okay. What do? They perform this job, Herb here. And Herb is a function object. And what they perform is this call operator. I will come to this async stream later, but anyway. And you see arrive and wait. And here's the key observation. I started the counter with 6. Each guy who comes to this point decreases the counter by 1. So it goes from 6, 5, blah, 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 but blocks here. And it continues when the counter here becomes 0. So first I wait until all are done with their work, and then I say, now you can go home. This is an extremely simple work synchronization. And here you see the output. David work done until you see it here, and now all are done with the work. Now all of them can go home. And say, wait exactly here until all are done. This is extremely simple. And once more, a latch only, when you would have more than one job to do, a latch would not do the job, you have to use a barrier. And with a barrier, you can also say, you have half-time worker and full-time workers, and the half-time worker can go home, and the next iteration only I wait for 3. I have more to it in my blog post, sorry, but I cannot go into the details here, because you see, C++, there's a lot of stuff involved. Okay, I'm almost done. Not almost, but anyway, I'm good in time. But I'm bad using my mouse here. Okay, with C++11, we have, C++11.20, we have the concept of cooperative interruption, meaning I can ask in thread, please stop. And the thread can say to me, I don't want to do it, or I want to do it. And this functionality is based essentially on a concept of a stop token and a stop source. Meaning a stop source can send a notification, please stop, and the stop token can read this notification and can react to it. And this functionality is built into gthread and condition variable any. But you can use it for any execution context or something which runs. Once more, I first thought it only works for gthread and for condition variable any, but you can use it for any stuff. So you have a stop source, a stop token, which you can ask, can I be stopped? And did someone requested me to stop? Once more, I send to you a stop signal, and then you say, now I have time. I look if someone asked me to stop. This is what you do here. It's cooperatively. I cannot force you to stop. I can only ask you politely. And I can only do it once to continue this picture. And this is the other part of the deal. We have a stop source. This is get token. This creates a token out of a stop source. Do you remind you this syntax about something we have with C++11? This looks or feels similar to a promise future pair. Really similar. We have here, it's called get future. You can also use a future only once or a promise. Same goes here. This is really quite similar model, at least for me. So here you get a token out of a stop source, and they are connected in some way. And then what you did with a promise in future, you maybe moved a promise to a different thread. Here you do not move them, you can copy them, which is a reference essentially. But essentially it works the same way. You have two things, and now you can copy one of the things to a different thread, and now you can send a notification. And sending a notification means request stop. And there's additional interface to it. You can ask if it's possible to stop, and you can ask if you already invoked stop request. Once more, you can do it only once. Let me show you two examples. First of all, a gthread. A gthread is an improved stud thread we have in C++20. And this gthread has kind of this interface built in for getting into notifications or for interruption. And have a look, I have two gthreads. One is I only use here a lambda, which is, sorry, I use a gthread which uses a lambda. And here you see I have a counter which goes up to 10. And if after each iteration, my thread sleeps for a fifth of a second, and then it calls not interruptible. And you see here, I implement a counter. And here I have a G thread which gets as first argument a stop token. Therefore, this G thread has the possibility to be interrupted because it has a stop token. And here's the run of the program. Now I start the program, you see. I sleep for 1 second. And here you see, non-interrupted, interrupted. Let me make it a little bit bigger. Where's my button? Sub-a-lot. I don't find the button here. Ah, here we are. You see, they sleep for a fifth of a second. So 5 times we see no interrupted, interrupted, no interrupted, interrupted, so nothing happens. Then in the main thread, I say, I send to both threads request stop. But only one of them reacts because only one of them has a stop token. The other will ignore it because there's no, how should I say it? No opposite part who could accept this stop request. And now you see, I say here, main thread interrupts both thread G-sets, but only the non-interruptible thread continues. The other thread, I just set here, return. When a stop token is, when this thread recognizes a stop token, it just says return. This was it for me. Once more, cooperative. You cannot enforce it, but you can politely ask it. And once more, this is not only due to a condition variable any or G thread, you can do it for anything which could run. Okay, let's see what I do here. I have a function which accepts as first argument a stop token, you see? And now I execute. And now what I do in this function, this is extremely simple. I just sleep for 1 second, and then I ask if someone requested me to stop. And here is my stop token. And see, this is the pattern you use for promises in future. You have a stop source, You create out of the stop source a stop token. You give this stop token by reference. Then you invoke this thread performing this function. This function needs 2 additional arguments. The first one is the stop token. Now this function has it. Here above, it can use it. And now you can here say request stop, which will send a notification to thread 1 and G thread. And this is all. Once more, I have a function, I have a thread performing something callable, which is a function. This function accepts as a first argument a stop token and a second argument a string. And when I now say request stop, you see, stop requested from main, thread is says stop requested. So you see, not much meaningful content here. And also G thread says stop requested. And you can also, you could even use it from a single-threaded program, which makes no sense. But anyway, there's just a mechanism to send a notification. Not more. And you can use it for anything which is running. You can also use it for a promise. A promise accepts a stop token, and you say, I request a stop. So for any runnable stuff, and only G thread and condition variable any have kind of a built-in interface for it. And now I'm almost done. Hey, this was good. No, oh no, two small features. You know, stud thread has a big issue. The issue is the following. When you create a thread, and this thread T here, as a local, goes out of scope. In the structure of T, you will get a stud terminate which causes a stud abort. It means you get an ugly error message. You have no idea what's happening. In GCC, in Clang says, terminate call without an active exception. I don't know what it means anyway. And here's G-thread. G-thread is modeled after Ray, meaning when G-thread, this is the improved thread, which G stands for joinable, but you can also say, it was also sometimes called E-thread for interruptible, but here it stands for joinable. This means when this G-thread goes out of scope, meaning T is a local, and the thread is still joinable, therefore no one called so far join or detach, it's automatically joined in this instructor. So you cannot forget to join it. It just lives as long as the scope goes of this small t. And now my last remark, which I will make short. Maybe you know it, stutz out is thread safe, but not in the way the most people think. Meaning when more than one thread writes to stutz out, there is no data race. It looks like a data race, concurrent reading and writing of something shared, but it's not a data race. What it is, you have to guarantee that each character is written atomically and that the character will appear in the right sequence. This is all what you have. So it could be a little bit of a mess, but it's not a data race, meaning no undefined behavior. And what we have with C++20 is synchronized output stream. Meaning when you write something to a synchronized output stream, it goes to a buffer, and when this buffer goes out of scope, it's displayed. And you know what? Additional application of Ray, resource acquisition initialization, such as G-thread is also an application of Ray. And here's how it works. You see, this synced out is a wraparound stutz out, and how long does it live? Exactly until here. And here the buffer is flushed, and therefore it's written out in a synchronized way. And you can do it even more on a temporary. You just make a wrapper for stutz out, and this temporary will live until this sequence point here, and therefore here the buffer is flushed, and therefore you will get a synchronized output. If you need synchronized output, this is the way to go in C++20.